Hello friend, welcome to Math A to Z. Our today's lecture is about basic of ring theory, and this is also in CBCS Mathematics Honors syllabus. Now we go to the main subject. In group theory, we consider a non-empty set G. Non-empty set G together with a binary composition star, and the algebraic structure G together with star is called a group if G satisfies the following property under star. The properties of group are: property A, star is closed, that is A star B belongs to G for all A B belongs to G. Property B, star is associative, that is A star B star C equal to A star B star C for all A B C belongs to G. Property C, existence of identity, that is there exists E belongs to G such that E star A equal to A star E equal to A for all A belongs to G. And the last property of the group is existence of inverse, that is for all A belongs to G there exists A inverse belongs to G such that A star A inverse equal to A inverse star A equal to E, that is identity. And these four properties together represent G is a group. But in ring theory, we consider the non-empty set. The non-empty set R together with two binary composition, one composition denoted by plus and other composition denoted by dot. These are not usually plus and not usually dot. This is a symbol and this is also a symbol. Now the algebraic structure. Now the algebraic structure R plus comma dot, that is the non-empty set R for ring together with two binary composition plus and dot is called a ring. if R plus, that is non-empty set R together with binary composition plus is a commutative group. This is A. So here 5 property. First property, for all A, B belongs to R imply A plus B belongs to R. Property 2, for all A, B, C belongs to R imply A plus B plus C equal to A plus B plus C. Associative. First property is closure property. Property 3, there exists 0 belongs to R such that 0 plus A equal to A plus 0 equal to A for all A belongs to R. Property 4, there exists minus A belongs to R for all A belongs to R such that A plus minus A equal to minus A plus A equal to 0. So this is the inverse property. Minus A is the inverse of A with respect to plus. And the fifth property is, for all A, B belongs to R imply A plus B equal to B plus A for all A, B belongs to R. These 5 property together represent that R plus is a commutative group. And property B, R dot, that is the non-empty set R together with the binary composition dot is a semi-group. That is property 1, A dot B belongs to R for all A, B belongs to R. That is closure property with respect to dot. And property 2, A dot B dot C equal to A dot B dot C for all A, B, C belongs to R. And these two property together represent R dot is a semi-group. And extra 2 property are required. Here C, 2 distributive law must hold with respect to addition and multiplication. That is, for all A, B, C belongs to R, 1 A dot B plus C equal to A dot B plus A dot C, and property 2, A plus B dot C equal to A dot C plus B dot C. This is the left distributive and this one the right distributive. So we say R non-empty set R together with 2 binary composition plus and dot is called a ring if R plus is a commutative group, R dot is a semi-group, and R follow 2 distributive law, left distributive and right distributive together with plus and dot. So a non-empty set R together with two binary composition plus and dot is form a ring if this 5 property, this 2 property and this 2 property, that is 5 to 7, 7 to 9, this 9 property fulfill, then R plus comma dot be a ring. Okay, this is the definition of a ring. Now if dot is commutative, that is A dot B equal to B dot A for all AB belongs to R, then the ring R is commutative ring. Commutative ring. Here the 0, that is the identity element with respect to the addition, is called the 0 element of the ring. This is called 0 element. Zero element of the ring. If in a ring R there exists the identity element E or I, usually denoted by I, identity element I belongs to R such that I dot A equal to A dot I equal to A for all A belongs to R, that is I be the identity element with respect to multiplication. Then we say that the ring R be a ring with unity. R be a ring with unity. Okay, so 0 is the 0 element, and if there exists identity element with respect to multiplication, then this is called unity element, and the ring is called ring with unity. And if the multiplication is commutative, then the ring is called commutative ring. If in a ring R plus comma dot unity element exists I, that is R be a ring with unity. With unity, then I must be unique. I must be unique, and this can be proved very easily. Let if not unique, then there exist two unity I and I dash. Okay, and from the definition of unity we can write I dot A equal to A dot I equal to A for all A belongs to R, and I dash dot A equal to A dot I dash equal to A for all A belongs to R. Now if we put I dash in place of a for in first relation, then we get I into I dash equal to I dash into I equal to I dash. And if we put I in the second in place of a in the second relation, then also we get I dash into I equal to I into I dash equal to I, because we put I in place of a. So from these two relation we say that here I into I dash and here also be I into I dash, and this result is I dash, but this result is I, so we must say I dash equal to I. So the unity is unique if unity exists in a ring or a ring with unity. Now we go to some example of a ring. If we consider Z set of integer, and we consider two operation plus and dot, usual addition and usual multiplication. Obviously Z plus is a group and this is also a commutative group with zero element is 0, and Z dot is a semi group because the multiplication of two integer is also an integer, and the multiplication of integer is whole associative property. So we see that Z and other two property of ring, that is the distributive property, is obviously whole in Z. So Z plus dot is a ring, and this is commutative ring because multiplication of integer is commutative, and this is a ring with unity because one with the unity of the ring. But if we consider 2Z or 3Z or 4Z, that is NZ, n not equal to 1 or minus 1, n not equal to plus minus 1, then this is the set of even integer. This is the set of integer which are multiple of 3, and this is the set of integer which are multiple of n. These are also a ring. These are also a commutative ring, but in this ring there is no unity because these are free from 1, but with respect to multiplication 1 is the identity element. So these are also a ring, commutative ring, but without unity. Okay, this ring commutative ring with unity, but these are all the commutative ring without unity. Now, if we consider Q plus dot, usual plus and usual dot, that is the set of rational with usual addition and multiplication is a commutative ring with unity. Set of real number, same commutative ring with unity. Set of complex number, same commutative ring with unity. Here unity is 1 equal to 1 plus I into 0, and here 0 element is 0 equal to 0 plus I into 0. This is the unity element and this is the 0 element. Okay, these are all the commutative ring with unity. Now we go to another example. Consider MNR. MNR is the set of all real matrix. This is for real matrix of order n. We know that MNR plus, this is matrix addition, is a commutative group. Here 0 element is the 0 matrix, n cross n 0 matrix is the 0 element, and MNR dot, this is matrix multiplication. Matrix multiplication is also a semigroup, but this is not commutative. Because the matrix multiplication, we know matrix multiplication is not commutative in general. So, and here one thing, identity matrix of nth order, of n order, n cross n identity matrix, that is 1 0 0 0 1 0 0 0 1. This is the identity element. So MNR plus dot is a ring, is a non-commutative ring, because multiplication is not commutative but with unity. This is the example of non-commutative ring but with unity. Now go to another important example. Integer modulo Zn, 0 plus 1 plus 2 plus 3 plus n minus 1 plus. We consider a particular example Z6, 0 1 2 3 4 5. Here Z6 plus 6, addition modulo 6, is a commutative group, because we know that A bar plus B bar belongs to Z6 if, or for all A bar B bar belongs to Z6, and all the 5 property of commutative group are held by Z6 plus 6. Also, here obviously 0 bar is the 0 element. Also Z6 dot 6, that is multiplication modulo 6, is a semigroup. Because this is closed under multiplication or multiplication modulo 6, and modulo plus always hold the associate property, and also the class satisfy or follow the distributive property. Here one class is unity and dot 6 is commutative also. So this is a ring with respect to plus 6 and dot 6, and this ring is commutative ring with unity. Similarly, we say that Zn plus n dot n, Zn plus n dot n is a commutative ring with unity 1 plus. Okay. Now we go to the example. Ring of Gaussian integer and the symbol is Zi equal to a plus ib such that a b belongs to set of integer. This is also a ring, a commutative ring with unity, because 1 plus I into 0 and 1 comma 0 belongs to z, and this is a complex number, so complex number multiplication is always commutative. Now similar ring of Gaussian number or rational number, and here the notation is qi equal to similar set a plus ib such that ab belongs to q. Okay, now we go to another important example. Ring of quadratic numbers, and in this ring, this is denoted by usually H. This ring contains the matrix of the form A plus IB minus C plus ID, C plus ID, and A minus IB. Okay, and here A, B, C, D belongs to R, set of real number, and this type of matrix can be written as A into 1 0 0 1 plus B into I 0 0 minus I, C into 0 minus 1 1 0 plus D into 0 I 0. Okay, and this matrix is usually denoted by I, this is denoted by J, this is denoted by K, this is denoted by L. So this type of element can be written as this is equal to AI plus BJ plus CK plus DL. Okay, and this is also a ring with respect to matrix addition and multiplication, but this is non-commutative ring. This is non-commutative ring, and this ring also contains unity because if A equal to 1, B equal to 0, C equal to 0 and D equal to 0, then this type of element can be transformed to I to 1 0 0 1 1 0 0 1, and this is the identity of the ring. This is the unity of the ring, and this ring is called the ring of real quaternion because this is belongs to real number and the ring of real quaternion. If this is belongs to Q, this is also a ring, this is also a commutative ring, this is also a commutative ring with unity I2. This is I2, and this ring is called ring of rational quaternion. And if this belongs to ABCD belongs to Z, this is also a ring. So from the one example we get 3 respectively: ring of real quaternion, ring of rational quaternion, and this last one, the ring of integral quaternion. Okay, so we get some important example of a ring. Now we consider another important example of ring, and this is the last example of ring we now give. We consider the set of all polynomials. The set of all polynomials like a0 plus a1x plus a2x square plus a3x cube plus an x to the power n. Okay, this is a1 x to the power 1, a2 x to the power 2, and here a0, a1, an belongs to R, set of real number, and x is the variable of the polynomial. This polynomial can be denoted by fx or gx or hx or otherwise, and this x is called indeterminate. Indeterminate of the polynomial. And here we define the sum of two polynomials as, let another polynomial g of x b0 plus b1x plus b2x square bm x to the power n. Now we define plus and dot as fx plus gx equal to a0 plus b0 plus am plus bm into x to the power m plus a m plus 1 x to the power m plus 1 to a n x to the power n if n greater than m equal to a0 plus b0 plus an plus bn x to the power n plus an plus 1 x to the power n plus 1 sorry bn plus 1 x to the power n plus 1 to bm x to the power m if m greater than n and if m equal to n then we get this is equal to a0 plus b0 a1 plus b1 into x plus an plus bn into x to the power n. Okay, and the multiplication, this is the definition of plus in this set, and the multiplication is defined as in general multiplication fx gx equal to a0 b0 plus a1 b0 plus a0 b1 a1 b0 plus a0 b1 into x plus x square a2 b0 plus a0 b2 plus here this also a term a1 b1 since x into x square a1 b1 and in the similar way, and this set is also form a ring with respect to the addition and multiplication, and this is called the polynomial ring over real number because the coefficients are all real. And here the identity element means unity element, that is the identity with respect to multiplication is I of x equal to 1. This is also a polynomial, and the property of this polynomial is fx into I of x equal to fx for all fx belongs to R of x. This is the set of all real polynomial, and the zero element is 0 of x equal to 0. This is the zero polynomial. Okay, this is the zero element of the ring. Now we go to some basic property of a ring. In a ring, 0 into a equal to a into 0 equal to 0 for all a belongs to R. In a ring, a into minus b equal to minus a into b equal to minus a dot b for all ab belongs to R, and minus a dot minus b equal to a dot b for all ab belongs to R. Okay, and we now prove these three results one by one. The proof of the first result. Since 0 is the zero element, so we have 0 plus 0 equal to 0. This is the property of zero element. Now a dot 0 plus 0 equal to a dot 0. We multiply a in both sides from the left, imply a dot 0 plus a dot 0 equal to a dot 0. This is left distributive law, and we get a dot 0 plus a dot 0 equal to a dot 0 plus 0. Okay, this is the property of 0, because a plus 0 equal to a for all a belongs to R. Now, since R plus is a commutative group, that is the group with respect to plus, so here the cancellation law, left cancellation and right cancellation law, both hold with respect to plus. So we cancel from these two from the left, and we get a dot 0 equal to 0. This is the proof. If we multiply a from the right, then we get this part, and similar process. Now we go to the proof of the second operation or second property. In a ring, for all B belongs to R, we know that minus B belongs to R. This is the inverse with respect to addition, such that B plus minus B equal to minus B plus B equal to 0. Now we operate A from the left. We get a dot B plus minus B equal to a dot minus B plus B equal to a dot 0, and this is 0 from the first law. So we get a dot B plus a dot minus B equal to 0 equal to a dot minus B plus a dot B. So we can write, or so we can say, a dot B is the left inverse of a dot minus B, or a dot B is the left inverse of a dot, right inverse of a dot minus B with respect to plus. So we must write a dot minus B equal to minus a dot B, because the inverse of A can be written as minus A. So inverse of a dot minus B is also written as minus a dot B, and this is the proof of second part. Now from this we get the third proof very easily. Here we replace A by minus A, and we get minus A dot minus B equal to minus A dot B, and from this property we can write minus of A dot B, and this is A dot B. This is the proof of last property. Okay. Now a ring R with unity I, then I must be not equal to 0. I must not be equal to 0, because if I equal to 0, then for all A belongs to R, for all non-zero A belongs to R, we have A into I equal to A into 0, that is A equal to 0. This is the property of unity and this is the property of 0 element. So A equal to 0. But here we let the A is a non-zero element. So we get a contradiction. So we must have I equal to 0. This is wrong. So I not equal to 0 in a ring or a trivial or a non-trivial ring. Okay. Now we go to an important definition or important part of ring theory. This is called, this is divisor of 0. Divisor of 0 or 0 divisor. We go to the definition of 0 divisor or divisor of 0 by giving a particular example. Consider a ring Z6 contain 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus. Okay, and we discussed earlier that this is Z6 is a ring with respect to plus 6 and dot 6. Here 0 is the 0 element and 1 is the unity element. Now if we multiply 2 plus and 3 plus, this is 6 plus, so this is 0 plus. Also if we multiply 3 plus and 4 plus, this is 12 plus, this is 0 plus. So here we get two non-zero elements, 2 plus and 3 plus, but the product of two non-zero elements is a 0 element. And also two non-zero elements, 3 plus and 4 plus, the product of these two non-zero elements is a 0 element. And this type of element, that is 3 plus is the divisor of 0 for 2 plus, and 2 plus is also a divisor of 0 for 3 plus, and similarly for 3 plus and 4 plus. But if we consider Z5 plus 5 dot 5, 0 plus 1 plus 2 plus 3 plus 4 plus 4 plus. Here we cannot get any two such element in this set such that A dot B equal to 0 for A and B not equal to 0. A not equal to 0 and B not equal to 0. So this ring contains no divisor of 0, but this ring contains divisor of 0, and the divisor of 0 is 2 plus 3 plus 4 plus, but here no divisor of 0. So this is a commutative ring commutative ring with unity and with zero divisor. Zero divisor or with divisor of 0, same. And but Z5, this ring is also commutative, is also with unity, and this is without zero divisor. Without zero divisor. And here an important thing, in the ring of in the ring with zero divisor is three class into 2 class equal to 0 class equal to 3 class into 4 class. Okay, so we can write 3 class into 2 class equal to 3 class into 4 class, but we cannot cancel 3 class from both sides because 2 class not equal to 3 class, 2 class not equal to 4 class. So we can say in a ring with zero divisor, the cancellation law with respect to multiplication is not followed, but the cancellation law with respect to multiplication is held in a ring also if the ring contains no divisor of 0 or a ring without zero divisor. Okay, I will come back soon with the second class of the basic ring theory. Thank you for watching.